Hey, what's up, guys? Chung here again. So today I want to talk about another LeetCode problem, number 430, flatten a multi-level double linked list. Okay, so you guys must have already known the, what is double linked list, right? So you have a previous and a next pointers, but what makes this problem different is that besides the previous and next pointer, it also has a child pointer, which points to the another child double linked list. And what it asks you to do here is to flatten this multi-level doubly linked list. So basically, one, two, three, four, five, six, right? Every time when you see another levels, let's say you traverse from one, two, and three, right? And then when you add three, you see, okay, I have a child linked list, and then you need to go down instead of go right. Then you go eight, right? And then you see, oh, I see another child. I'll go down here, 12, right? And then you come back here. You go 9, 10, 4, 5, and 6. That's uh, that's how you traverse the flatten this linked list. And in the end, you have 1, 2, 3, 7, 8, uh, 11, 12, 9, 10, 4, 5, 6, right? So and so today I'm gonna like introduce two solutions here. So the first one is using a stack, and the second one is using a recursion. Mm, yeah, you guys can choose whichever method you guys prefer. I think for me the recursion is more intuitive, but it requires a little bit more codings, and the stack is kind of like also intuitive, but you gotta think it in a different way, right? So let's start with stack here. So since we need when every time when we see like for example here, right? For example, you have one, two, three, then it's fine, right? So let's say we have three here, and then we have four and seven, right? So what so we're gonna push, right? Basically every time when we see a next, we push. We see a next, we push this node into into the stack, and then we pop from the top, right? The reason why we use a stack here is like say, let's say if there's only a next here, so every time we add, we push, and then we pop, we push, we pop, right? And then when we at three here, we see a four here, right? And then we push four into the stack, and then we see a seven. If there's a child here, and then we push seven, right? We push seven here, and then and next time we pop seven, and then we go from eight. So the reason we're doing a stack, so stack is most likely using to store the path, right? So what you have seen before, right? So just like how you traverse the tree, right? If you do like a tree traverse, like the pre-order, no, sorry, the in-order traverse, right? You do it in-order traverse, you use stack. Every time you see like a node, you push it into the stack, and then that's how you remember what had been visited before, right? So same thing here, similar idea here, right? So we see a next four here, and then we know, okay, so once we finish processing all the child lists, we need to come back to four. That's why we use a stack here. Basically, we push four and seven, right? And then, okay, next time we pop the seven out, right? And then we see eight here. And then we see, when it goes to next, we see eight. And then when you see eight here, okay, sorry. So once we pop seven, we see the next is eight. And then we're gonna push eight here, right? And then we pop eight, we see, yes, we pop eight, and then we see a 9 and 11. So and then we push 9 here, and then we push and then 11, right? That's how we keep the sequence of the node we need to process. Basically, once we process everything here, the next one left will be 9, right? And then from 9, and we keep continue doing it we uh until we're at 4 here, and then we just keep processing it. All right, so let's do it, right? Uh, let's do uh, since we are going to maintain the a root here, I'm gonna use a root to be the return value here because return root. Because in the end, because once we uh, uh, I mean pop this head here, this value might be changed, right? That's why I'm using the uh, that's why I'm using this thing here, using another root here. So what we need to do here is, right, so since every time we're going to moving forward, right, moving forward, and we also need like a pre variables to define what was the last node here, right? So that we can every time we pop a node, we can we can link those two together, right? Because for example here, like let's say after once we pop 10 here, right? Once we pop 10 here, and then the next one will be 4, right? So there will be a moment, there will be like 4 here, and then 10 here, right? So once we pop 10 here, the next one will be 4. And when we are at 4 here, we need to link this 10 to 4, right? That's how we link these two together. And in order to do that, when we are at 4, we need to know what was the last node we popped, right? That's why we also need a pre node here. You know, for this pre-node, we can use, okay, let me finish the code here. Stack equals, so basically we start from hat, right? And then we do a while stack, right? While stack, right? And then the current equals to what? Equals to the stack dot pop, right? So with a pre here, you know, we can either use like a pre with the non-values, or we can use a dummy header, right? Dummy header, we basically dummy header points to the header, so we don't have to worry about this root thing. We just need to do some final cleanup thing. But in this case, I'm not using a dummy header here, so I'm just stick with the original header here. So okay, so I'm gonna write the main structure here. Basically, like we said, if this current has a next, right? We push we push this current next to it, right? And then if the current has a child, we push the child to it, right? And then in the end, we keep moving this current to the current next, right? That's how we sorry, I'm sorry. So not this one. Sorry, I my mistake. So in the end, we update this current with the current with the last popped node here, right? So so basically every time when we pop this thing, what's gonna do? Oh, sorry. So I yeah I went too fast. So here every time when we find a child here, since we need to we're gonna remove this layer. We're gonna flatten it. So every time when we see a child here, we just need to I mean basically remove this child pointer, right? And then okay, so now once we have a current, right? Assuming we already have the pre here, so basically we do a pre dot next equals to current, right? And then current dot pre equals to sorry, pre equals to pre, right? But since I'm not using a dummy here, so the first time when we pop the head, the pre is none. So I just use a simple check here. So if pre is not null, then I do this, right? see, do I really need this root here? The head, we pop the current next, current equals to pre, yeah. What if I, okay, so anyway, so let's try to, so basically that's it, right? So we just maintain like um, a pre node here, and then every time we see a next, we push, and then the the sequence matters here, right? So and then we see a child, we know, okay, we want to process this child first. In the end, we just return the root here. Uh, push. Sorry, append. Yeah, that's what happened when you when you're coding while talking. uh, fine. If not had, right? Return none. Cool. So let me do a quick check here. If I just return had, will this work? Yeah. Yeah, still works. Yeah, sorry. So yeah, I think the thing is here because we are not changing this had, right? We just simply assign this one to current, and then we do a current with this. So yeah, yeah. So in this case, we don't really need this root here because we are not changing this current because we pop this and we assign it to current, right? And yeah, so this thing should just work. Cool. So okay, so basically that's it for the stack solution. Now let's make it more interesting. How about the recursion, right? Okay, so I'm gonna just comment out this thing here so that we don't lose our precious code. So with recursion, okay, so what does recursion means, right? So let's continue our like traverse here. We see a one here, two, nothing happens, right? And three, right? Basically, when we add three here, we see, okay, there's a child linked list. So we'll do a recursive call of our helper functions, and we're gonna get basically the helper functions will return us the entire list of the child linked list. But keep in mind here, so once we other besides the head, we also need to know the tail of that sub-linked list, right? Because not only we need to link this 3 to 7, but we also need to link this 10 to 4, right? That's why within that for that helper functions, we need to return both the head and the tail, right? So that's the only thing you need to be to to be careful. All right, so let's do it. All right. Okay, so let's do it. And all right. Mm, yeah, helper functions, helper, right? Do a helper, and then it's gonna be the hat, right? So okay, so let's say pre-current. Mm, So like I said, same thing here. So while do I need the current? Yeah, so in this case, we need the current here of the hat because later on we'll be changing this current. And then so okay, so while current, right? And then we return we return the like I said, we return the hat and the tail. All right, but we'll okay, so the tail will be none at the beginning, right? Okay, so let's check this. So okay, so this thing will basically will keep moving it to the keep moving it. So this one is going to be current next, right? So that's how we keep moving forward, and that's why we need to define like a new variables here instead of using the head, because here we'll be updating the head, right? That's why we need to. Sorry, I'm repeating myself. All right. So and basically, if nothing happens, if there's no child, we just keep doing this, right? But the thing we want to check here is, oh, and one more thing. So how can we get the tail, right? So the way we're getting the tail for the node is we just simply we every time we just update tail, basically just like as if we are maintaining a pre variables here, but I'm calling it the tail here. Basically every time I'm updating it, so by the time this current is empty, we reach the it's none, we reach the end of the tail, and the tail will be the current tail will be the last node, right? Because we update this tail with the current node, right? And okay, cool. So if there's no child, that's how we traverse this thing. But now we need to take care of this no this like this bad guy here, right? If current dot hides a child, right? Then what do we do? We we do a recursive call, right? So basically we do a helper, right? Helper dot sorry, with the child current child node, right? And then like I said, we'll then after making this call, we'll be getting two variables here, child head and child tail, right? And then same thing here, right? Remember, we need to remove this child link here. Dot child equals to none, right? And now since we have the head and tail, we can basically we can link these things and right, we can link those two. The way we're doing it is pretty straightforward, right? So uh current yeah, so current dot next equals to the child head, right? And the child head dot previous equals to the current, right? That's linking 3 and 7. And now let's do a 4 and 10. The 4 and 10 gonna be the child tail dot next equals to current. Oh, sorry. Since we also need like a temp temp dot next temp next equals to current next, right? Because and once we assign this the child has a current next, we'll be losing the this 4, right? That's why we need a temp next here. So and then here we just do this, right? And then same thing, temp next uh, dot previous equals to the child tail. Oh, and I think one thing to be noticed here that this card next it might be the last one, right? So this temp dot next might be none, right? Because let's say there if there's a linked list, there's a like if there's a 1 2 3, right? And then there's nothing here. And then there we have a linked list, 7, right? 8 and 9, right? In that case, there's nothing here. There's none, right? And we're still trying to get this current next. In this case, the temp next will be none, right? And here, if we do a temp next dot previous with the child tail, which is 9, then we'll have like the what the non exception, like the non-reference exception, right? So that's why we need to do a simple check here. And if temp is not null, right, then we link those things, right? Because here it doesn't really matter, right? Here, even though this is none, the next none, the child next equals to none doesn't, it won't affect the final result, right? So that's that, and let's return, right? Let's just do a return. So now we have the helper functions, and we just do a cal helper dot head, right? And here it will give us two results, two element, head and tail. And in this case, we just need head, right? So that's how we do the recursion calls. See, passed. All right. So and yeah, just do a real recap here. So first the stack. So we use a stack to track uh, what are the nodes we need to be processed next, right? Since the ones we pushed earlier will be popped the last. That's why we every time we see a next and child, we push we sorry. That's why I made this mistake. I append this child last. That so that we can be sure we'll be processing this child branch first, right? And then then we have this like recursion call. So with the recursion, the key idea here is that we not only we need to return the head of the recursion method, but we also need to return the tail so that we can link the head and also the tail, right? And in the end, we just return the head. And cool, I think that's pretty much it is about this problem. Yeah, I hope you guys enjoy watching the videos. And yeah, thank you so much for watching it. And I'll be seeing you guys soon. Bye bye.